First of all, my name's Gary Frost. I'm an architect in the Java platform group at Oracle. And I've spent the last 10 years trying to get Java to efficiently run code on GPUs. And the question that's, like, spoiler alert, the question, are we nearly there yet? The answer is, yes, we are nearly there. But let's walk through this. It's been a passion of mine to get this working, and a lot of technologies have aligned recently which are enabling us to do this. So that's me. This is what we're going to talk about. We're going to talk a little bit about Java plus GPGPU, what it is and why we might want it. Also, a little bit of history, an introduction to HAT. So Paul talked a little bit about HAT earlier when he was talking about Babylon and the AI technologies we were leaning on. And then under the bonnet, because obviously it's a HAT, we'll show you a little bit about how Babylon works, how we're using Babylon and Panama to actually get to the GPU. And then I'll give a walkthrough of the programming model, how you might use it. And then we'll look at some examples, demos, which if the demo gods are working well, we'll be able to show some nice performance uplift from using the GPU on this laptop. And then talk about future plans and ideas we have for enhancements going forward. Okay. So first of all, the general purpose programming for GPUs has actually been around for quite a while. The early 2000s, people started to do crazy things with shaders that are normally used for pixel rendering for games. And they decided that if they kind of passed the data, blocks of data across, pretended it was a bunch of vertices for a shader, do the compute, and then actually display it, but pull the data back, they could actually get the GPU do some useful work for them. This started to get formalized, the shader compiler technology, and then a little bit later on, CUDA came out and OpenCL came out. And since then, we've all been able to program GPUs sort of as we would using a C99 style programming language. And in a weird way, two things have come out of this right from the beginning. Is a new way of programming that came from shaders, and that was we split our work into kernels, and we exposed this thing called an ND range programming model, and we're going to take those two paradigms and bring them into Java later on. Why we might want to do this, this is a nice chart which goes all the way back to the year 1995, so I'm trying to line up with the JavaOnes. As you can see, this is actually the top 500 computers in the world. The red line in the middle is the fastest computer that year, how many teraflops it was able to run, log scale on the side. So we've got Moore's law popping in for us here. What's really interesting, so the yellow line at the bottom is the slowest of these machines, and the blue line at the top is if we actually took all the compute from all of the machines that year, the blue line represented that compute. If you went to Fry's, you could actually buy a nice GPU that if you could teleport back to the appropriate year, you can see that it intersects with these charts. So for a few years back in the early 2000s, that one GPU would be in the top 500 supercomputer list for that year. GPUs are fast, and they're certainly on any of the platforms we're looking on today. There's a lot of computing power in there. It's just trying to get hold of it. And in fact, just to tell you, this laptop that I'm running on, which is an Apple M1, it would also sit on that list quite comfortably. So again, we've got raw power, we should start to use it. It'd be great to be able to do it from Java. So what I'm going to talk about today is Heterogeneous Accelerator Toolkit, which is actually a project within the Babylon project, which is what Paul was talking about earlier. And Babylon is our attempt to be able to take Java code and move it into foreign runtimes. So the particular runtime we have in mind here would be like a CUDA runtime or an OpenCL runtime, something that can get us off to the GPU. So how does the toolkit for targeting such devices? It basically exposes a GPU-style programming model to Java programmers, an ND range style programming model, but we can put other programming models if we wished. We also are going to expose what's called a compute programming model. So since 2008, people have been playing with Java bindings for GPUs, and they've been able to write little kernels and get them to run quite quickly. But for you to get real performance, out of a GPU, it's not enough just to run a kernel fast, come back to Java, run another kernel fast, come back to Java, etc. The real trick to get GPU performance is to try to get a view above this. If we have many, many kernels we want to execute, we want the vendor needs to be able to look at the flow of the kernels being executed and the data moving between them. And so we actually introduced another layer of programming, which we call the compute programming model, which we'll talk about a little bit later as well. We also realized we don't want to pick winners and losers in this world. There are vendors, CUDA, there's the NVIDIA, there's the AMDs of this world, the Intels of the world. They all have their own backends for accessing their GPU compute. We don't want to get in that game, so we built a plug-in abstraction for the vendors to come along and plug in their particular goodies into the backend. We'll provide the Java interfaces that you code against. We'll create a lot of the Java infrastructure to get you to the backend. But hopefully, if we do this right, NVIDIA comes along and writes a CUDA backend, Intel comes along and writes a backend for its particular hardware, and so on. One of the things we're really leaning on top of, though, and one of the things that made GPU programming from Java difficult early on, was Panama. Panama's FFI and FFM. And again, we've heard about these before. Panama allows us now to sidestep JNI, which was always a problem, and have a more natural way of linking up with C-styled libraries. And we leverage that a lot. Also, Panama offers the ability for us to use off-heap memory. So we can now ask the GPU, where would you like to allocate this memory? Where's the best place for you to allocate it, rather than us picking the wrong place and then force copies. Anytime you copy data, you kill a puppy in this world. So we don't want to kill any puppies. So this is the sort of heterogeneous toolkit. This is where it plugs together. You write your application code on the top, which uses the HAT APIs, which we're going to talk about later on. And that sits on top of the JVM, on top of the GPU and the FPGA, whatever your final target is. And we've got this thing called a plugin, which somebody will implement it for you. I've created sort of reference implementations, if you like, for a CUDA backend, for an OpenCL backend. We also have one for a PTX backend, which also works for NVIDIA. But also, we have a Java backend, because one of the cool things here is if you write a Java backend, you can check your logic in the IDE of your choice and actually single step through your Java code to make sure your logic is correct before you commit to trying to run it on a GPU. Debugging on a GPU is a non-trivial activity. So by having a Java backend, we allow people to test that their code runs, even though it may not run as performant. Hopefully, it won't run as performant as it will on a GPU. And so here we show how we might get different vendors bringing their own backend in order to come in. One of the interesting backends is the JavaOne we mentioned earlier. Paul also mentioned in his talk earlier about Babylon, and also, talking about the Vector API. It's very possible we could target the Vector API as a backend to HAT. So you could write your code as if you were going to write a kernel, and we will actually vectorize it down through the Vector API. So I talked about a couple of notions, kernels and ND range. What does this mean? So this is not too foreign an activity, truthfully, if you'll follow these logical steps. In the past, we've written loops over code, and they look very much like, hopefully you can see the code at the top right. It's a bit of a squint. But it basically, we've had loops. We understand what they do, and we've had them in Java for a while. If we were to take the body of a loop, which is a simple loop like this particular loop just squares each value in a particular array. If we were to take the body of that loop and wrap it in a method, and that method would actually take the array that we wanted to square, but it would also take the index that we're trying to square. Does that make sense? And then we called it within the loop. We started to make the notion of a kernel. The kernel has a few traits, some interesting flavors. First of all, we have a method that accepts uniform data, the arguments that we're passing to it, and also some notion of identity, which lane we actually wish to execute on. In this case, we're using I for that. Truthfully, for a kernel to truly be a kernel, the order that we actually execute this loop should bear no bearing on it whatsoever. So your kernel cannot depend on the order of somebody else running. The only piece of information you're allowed to access is your own identity. then if you've written this, you've actually written a method which looks like a kernel. And so we could choose to call it now within the loop that we had above, or we could run it backwards, because we said it's not allowed, you must make sure that your kernel still creates the same result if we run forwards or backwards through the loop, or in any random order. I could take an int stream of random numbers, and I could actually pass them in as the indexes, and it would still work. So here we are, instead of using a loop, we're going to use an int stream to create each of the indexes that we're going to use. We don't require a loop to be created for us. We can just use a lambda and sit within the lambda. And you can start to see why this is a parallel-friendly environment, because if we put parallel in this stream, now our code can run in parallel, can run in multiple threads in the Java world. And in fact, back in 2012, when we started the Sumatra project, this was the programming model that we exposed for people to write code for the GPU. The Sumatra would find these patterns, and it would head them off to the GPU. I just want to explain a little bit about how HAT uses other technologies, because truthfully, it's the other technologies that make all this worthwhile. Babylon is a big part of HAT, and Panama is a big part. First of all, Babylon. Previously, when we've worked with trying to execute code on GPUs, we've had to lift code from bytecode. So we compile the code, we might compile a kernel, it goes down to bytecode, and then we have to lift intent back out of the bytecode to try to generate the code that might go off to be OpenCL or CUDA or some other code. Babylon allows us to meet halfway. When the Java compiler compiles code, as Paul mentioned earlier, as we saw in the keynote, there's a model squirreled away in the class file. We can lift that model out. That model is ideal for us then to retarget to, for example, turn it into a kernel that's going to run CUDA code or a kernel that's going to run OpenCL code. So we actually lean on top of Babylon quite a lot. A, to create kernels, and secondly, we also use Babylon to analyze the code that's calling the kernels, which I call the compute method. We'll see later on why that's important. But there's another layer that we've introduced, which is you have normal Java code, you have compute code, and you have kernels. And by exposing that compute middle layer, we now get to extract real performance out of the GPUs, because we know the order in which kernels are going to be executed. The thing that's really interesting is, we've not mentioned earlier, is that Babylon not only can give you a code model, you can transform that code model into some other code model, but right at the end, you can say, okay, I'm done with it now. Let me generate bytecode from this, and I'm going to run that version of the code. That's one of the things that makes code reflection really interesting, because you can take the code model, do something with it, inject code, remove code, move it around, then you can create bytecode out of it and just execute it like it's any other class. The VM can run it. From the Panama project, we've inherited two useful technologies. One is the FFM, FFI stuff, which is like an easier than JNI way of writing native code. So people can now write backends for us. These pluggable backends, they can write them without having to use JNI. They can, if they wish, just use the FFI interfaces. They can, in fact, use JExtract. So again, we've talked about JExtract earlier. With JExtract, you would just point JExtract to your OpenCL header, for example, or your CUDA header, and your library, and it will generate you a pure Java implementation so that you can talk to those particular libraries. And so basically, JExtract allows us to build backends without having any native code at all.
Where do you deploy those?
Pardon me?
Where do you deploy those?
They'll be deployed onto some sort of backend, like a GPU or an FPGA maybe. And the GPU is going to execute them. Sorry. We'll talk about. Hopefully we'll answer that question in the demo. And the other thing that Panama gives us is a way to communicate with with other libraries and with the GPU and the vendor using off-heap data. So we all know in the Java world, we're used to our objects being on the Java heap, which of course the garbage collection can move around and do whatever it wants to do in the background. That's fine for Java. When we're talking to a runtime that requires data to be in particular locations, that doesn't work for us. So we have to allocate memory in off-heap space. And that actually means if we can allocate in off-heap space, we can actually ask somebody else to allocate for us. So in our case, we can actually ask the GPU, where would you like us to allocate? Where's the best place to allocate to avoid copies? So we can actually ask the GPU to allocate for us, and then we'll just take it as a blob of bytes and move it around. And so Panama actually gives us two things: memory segments, which are essentially blobs of bytes, and a memory layout is a way to describe what those bytes represent. If you imagine, it might describe a structure or an array of structures or an array of ints or an array of floats or some nested data structure that you've created. What we've done with HAT is to simplify that process. And so, for example, if you wanted to describe something that we're going to use on the GPU that was just going to be an X and Y position, it was just a point, what we do is we describe it as an interface. So it's an interface representing a struct. It has an X and Y accessor and getter, and that gets turned into a struct on the GPU, which is on the right-hand side. So you just create yourself an interface, and providing it extends a HAT buffer, then HAT knows what it needs to do in order to get that out off to the GPU and allocate it in off-heap. Just to bury down into that a little bit, we have this interface. It's equivalent to this struct. We kind of have to do some work to order them because the order of methods is not defined, and so therefore we have to actually impose some order. We may even have to impose some padding if we're talking to an API that currently exists. And so we would actually, in order to allocate one of these little point things, we would ask our accelerator, which is our GPU vendor's backend, to allocate it for us. And so again, we now set it, but we're using the calls on the interface to set it, and we're using the calls on it to access it through the interface. So we have a way of expressing a complex structure just by using interfaces rather than without having to have builder-style patterns. And we wrap all this normally inside an interface. So this is an interface for X and Y. The schema builder is wrapped inside the interface itself, and then the factory for creating it is inside. So we would just go and say, go to this X or Y and create one for the ask this accelerator to create one for us. That's probably detail that we don't necessarily need, but this sort of gives you an idea of how we would describe an array of ints, for example. We're describing an off-heap array of ints. And we basically say it's an S32 array, it's got a length field, it's got an array field, which actually got the bodies inside. The schema defines the order and the relationship between the fields. We have a creator in there. And again, we can create a 200 element S32 array, and then we can set and get individual elements from the Java side using the API on the left. On the right-hand side, we can see how the C99 CUDA code or OpenCL code, when it accesses it, just treats it as a struct, and it just treats it as a pointer. So looking at our example earlier, we had a square example where we showed what it might look like if we were having a square kernel. This is actually what the square example would look like if we were to write it using HAT. So we would have a class. We would have a method, which is our kernel method. In our case, we've got a square kernel. And we're going to pass it an S32. We can't use an array because that's on the heap. So we have to use one of these off-heap constructions that we just manufactured. And we actually pass it something called a kernel context, which is where this kernel gets its identity from. Remember we said earlier, a kernel gets its identity from something. Which part of the work am I going to work on, which is different from somebody else? And so here's the code for the kernel method that we described earlier when we were describing what a kernel looks like. And then we also put in the same class by convention, a compute method. This one, in this case, because we've just got a single kernel, all it does is dispatch the kernel that's also in the same class. So here, we're going to call the compute method. We're going to pass it our array. That array is going to dispatch to the kernel's going to do the work, and then we're done. But there's a compute layer, and there's a kernel layer. And then in order for us to execute on a particular device, we say, go and get an accelerator, for example, for a GPU. Go and get an accelerator for a CUDA GPU, for example. And after you've got the accelerator, you ask the accelerator to actually compute the compute method. The compute method itself then will go up and call the compute method, which calls the dispatch on the kernel. So we've kind of broken our code into sort of three strata, three layers of types of code. We've got our kernel code, the stuff that's going to run on the device, the GPU device. That kernel code, by the way, is going to have major restrictions on it. You can't be calling system out .println on that code, because this code has to run on the GPU. So it's going to be limited to computational arithmetic operations, accesses to the buffers that we've passed to it. But that's pretty much all you can call it. You can't allocate. You can't for exceptions. This is going to be restricted code, but this is where your math is coming in. This is where your compute code is actually sitting. And then the compute layer itself, this doesn't have any restrictions. However, you can negatively impact performance with particular patterns that you run. So this is where the smarts come in. You have to understand how you want to run your code and what the kernel looks like. And then there's just regular Java code. So in reality, what we've done is we've split the world into these three different types of code: just normal Java code, compute code, and kernel code. The compute code, by the way, is interesting because it's not necessarily going to be run by the Java virtual machine. The Java code will be run by the Java virtual machine. The kernel will definitely not be run by the Java virtual machine. The compute code, it's up to the vendor to decide how it wants to run that code. Because what we did was we passed it a model of this code. We don't care. It might turn it into bytecode and run it. It might interpret it. Might turn it into C code. Might do whatever it wants to do with it. We're expressing our intent through the compute model. So let's look at an example. This is a healing brush example. Healing brush is how you get rid of people from photographs that you're... So you might have seen something like this in Adobe. Sorry, let me back up. I apologize. I'm going to run it, first of all, with the Java multi-threaded backend. Okay, so the idea of the healing brush is you kind of pick somebody that you would like removing from your picture. And what's actually gone on there is the algorithm's kind of cute. The algorithm takes the outline of that particular thing, and it looks around the whole image to see what's the closest match that I found to that particular outline, and then it infills the data from that location up. You'll notice at the top left, the search here took 883 milliseconds. If I pick something larger, that search can get quite considerable. And there's another thing. Remember, it's just interested in the outline. There might be something already in the outline, which is what's happened in this particular case. But look, the search here was like over 3 seconds for it, because it's basically scanning the whole image to try and find the best match. Here we'll run it using the OpenCL backend. Now, interestingly enough, the first time we actually call this, it actually is when it does all the work that we talked about earlier, where it's converting the code. So it took 205 milliseconds in order to do that. But now it's pre-compiled all the code. So the first time you hit a kernel, it has to go through this process of offloading. You work out where it's going to go, analyze the model, and do all of that work. But once it's done it the first time, so for example, this one, which took 3 seconds previously, we can now do it in 41 milliseconds. Just because well, it should be no surprise, GPUs are pretty good at looking at images, but this is a good representation of the sort of workload that we can perform. I'm going to go on to another demo. So this one's a bit more complicated from a compute point of view. This one's a face detector. Now, a face detectors are notoriously tricky to do on the GPU because this particular one is a half face detector. It's a cascade, a tree that you build of half features. These things at the bottom, these black and white rectangular areas are called half features. And the way in which you detect a face is you can imagine that there's a tree of things, one feature that is two black dots either side of a white space. That sort of matches the bridge of your face here. If you find one of those in a rectangular image, well, you continue down the tree on the right-hand side looking for other features. If you ever fail, then you've failed the cascade. And so you scan the whole image, making little rectangles, and what you're trying to do is to get through the whole of this tree. This tree is huge. It's not as simplistic as these little areas here. So I'm going to step back to the demo again. Apologies to the guys at the back who have to keep switching over. So again, we'll do we're going to just run the Viola Jones. And so this one's actually going to run 10 times. You can see it takes about 1.7 seconds. It's going to run it 10 times just to amortize the cost. But you can see it consistently takes about 1.7 seconds in order to scan the image. And then right at the end, it detects the faces. If we run that same code, well, if we could do that, oh yeah, sorry. You'll see now that it's able to now process so it's still done it 10 times. This time now it takes 82 milliseconds instead of the 1.7 seconds. So this is a workload, even though it's showing you visually what it's doing at the end, it's not just an image processing problem, which GPUs are good at. This is a data processing problem, which is falling through that cascade in GPU memory. Okay, I'll go back to the presentation. So we're going to look at this later on. We're going to look at the game of life. Is another demo I'm going to do later on. I'm not going to show you now. Well, I'll show you the Java version later on, and I'll show you the GPU version. But I also want to use it to highlight a particular problem that we have. So this is the game of life. We've probably all seen the game of life in one stage or another. But that's the kernel on the right-hand side. That's just pure Java code that's running the game of. That's the hat implementation of the game of life. Here's the algorithm, but basically you run through a grid, and for each element, if it's got the appropriate number of neighbors, sometimes it dies, and following the rules, sometimes it stays alive, and things die of overpopulation, or they spontaneously come into existence due to reproduction. But this really answers the question we earlier on the question was, why are we exposing this compute model? I understand the kernels, I'm going to send them off to the GPUs, and we want them to run fast. But as I mentioned earlier, just being able to execute the GPU kernel is not going to get you peak performance. It'll get you some performance, but it won't get you peak performance. You're going to get optimal performance when you're able to trace the minimum number of copies of data back between the GPU and the CPU. You're trying to find how to minimize those buffer transfers. And by providing the backend, the vendor backend, access to the model that's calling the kernels, it gets a visibility over the data paths and also the control flow. And so I'll give you a really bad example of somebody writing a piece of code. This is a weird kernel. I've got an ink kernel, and I pass it an array, and it will add 1 to every element in that particular array. And this is like a fundamental building block. And let's say I wanted to not only have an ink kernel, but I wanted to actually add a number to every element in an array. Well, one really inefficient way of doing that is to actually call the ink dispatch within a loop. So I call the ink dispatch, whatever the number of add was. I just call the loop dispatch and it's going to go over it. So essentially, by the way, this is not how you write kernel code. This is showing a bad example, but it highlights an interesting point. A naive implementation, if you go back and look at some of the stuff from the late 2010s, naive implementations of early Java bindings are forced to move the data to the device and move it back before and after each kernel is dispatched. So it's as if we wrote the code below. It's as if we wrote the code and said, well, we're going through a loop 10 times, move the data to the device, perform an inc, move it back from the device, move it back onto the device again, increment it, and move it back. You see what I'm saying? That's not the most efficient way of solving this particular problem. By giving the back-end visibility over this code, the compute code, it can work out, wait a minute, this guy's calling inc 10 times. I can either enroll the loop, for example, or I can at least leave the data on the GPU because he's not doing anything with it back here in Java land. So essentially, a smart implementation of a backend would take the compute code and would essentially say, well, I'm going to move the data to the device once, I'm going to loop over it 10 times, and then I'm going to move the data back at the end. Does that make sense? So that's why we want to expose the compute method to the back end. And actually, the game of life actually has this problem. We can create, you'll see in a moment, we can create generations in the game of life faster than the display rate that we can show in swing. And so what will actually happen is if we just copy the data backwards and forwards, we'd be forever waiting on swing before we generated the next generation. So this is the sort of loop we may actually construct. This is the compute method. We might say, whilst the viewer is still running, dispatch the kernel. The way in which the game of life has to work is you have to take one whole generation and copy it to another generation. You're not allowed to partially do the work. You have to have a complete generation move from one place to another. The way we solve that problem is we oversize the buffer. We make it twice as big as it's supposed to be. So on each generation, we move the data from the top to the bottom of this particular buffer. That kind of makes sense. So instead of, we've really got two buffers, but in one blob of memory. And so what we're doing here is we dispatch the kernel, we flip the to and from, because we're going to go from top to bottom to top on each generation. And then only if the UI is ready for us to update it, do we then bother updating the grid. This means that if we can generate generations fast enough, well, we don't have to bother copying it back from the device at all, because we can just stay in the loop without the update. And the once in a 20 frame times when we actually have to generate data, well, then we copy it on that occasion. And so again, it's almost like by analysis of the code, by static analysis of the code or dynamic analysis, we can kind of say, well, the grid needs to definitely be copied once. The control block needs to be copied once. We know that's for sure. We do need to copy the control information back from the device because we just flipped it. You remember we flipped the to and from, so that definitely has to come. That's going to have to go back onto the device. But we only have to copy the grid data if we get into this conditional loop. And this is the sort of working out that the vendor can do because they have the compute model. And I'll now try to demonstrate. And this is the actual code we're going to run. This is literally the code we're just about to run inside the Game of Life demo. So I'm going to go back to the demos. So I'm actually going to run 3 versions of this one. Well, I guess it doesn't matter that I leave that there. So first of all, this is a big Game of Life world. This is a 10,000 by 6,000 grid, which means in order for you to be able to see the individual dots, that we've got in here, we kind of zoom in. I'm going to actually run it. So remember, we're running on a Java backend. This is multi-threaded. And you can see we can handle 2 frames per second on this particular piece of code. I'm going to exit out, and then we'll run it using the OpenCL backend. Oh, excuse me, we're not going to do that because I want to turn something off. Okay, so now we're going to show what this code would look like if we didn't give the backend the opportunity to minimize the buffer transfers. So you can see, actually, I just messed up clearly because I've shown what it looks like. Okay, spoiler alert. For some reason, this is messed up, but we will actually only manage 50 generations per second. 50 is much better than 2, so we started off with 2 generations per second in the Java world. We're now in minimizing the buffers, which actually means we can get around, well, we'll eventually settle around 200 frames per second. And you can now start to see that this game of life is it's actually an implementation of a digital clock using the game of life to represent the circuit. So it's actually going to fill in the digital clock. And then in a little while, this 0 on the end here will flip over to be a 1. Thankfully, game of life is Turing complete, so you can actually implement algorithms using the game of life, and that's what this has an example of. So we've got a huge number of generations coming up here. We're now managing to sustain 157 generations per second. Yes, generations per second, whereas previously with Java, we could manage 2. So that answers the question, hopefully, what sort of speed up can we expect from various algorithms? Going to go quickly back. I've only got a couple of slides to follow through on. So what have we looked at? We introduced the notion of general purpose GPGPU programming from Java and a little history. We showed the Heterogeneous Accelerator Toolkit. We show how HAT leverages Babylon and Panama to do all of the work. And we also showed how by exposing the compute method, not just the kernels, we're actually able to get a lot more performance than we would have if we just had just exposed the kernels. There's a lot of work to do here. We're still working on the minimizing the buffer transfers, even though we've got a good lift in performance. I know in that particular example, it's still doing 2 copies that it doesn't have to do. And I'm determined to get rid of those 2 copies. Also, I'm considering moving all of the backends. At the moment, the backends are written in native code. I'm considering moving to JExtract for all of the backends. It just makes building code a lot easier, because at the moment, the build for HAT requires me to include CMake so I can build native artifacts. And if I use JExtract, I just have to use Java-C to build everything. Got a test across the various backends and platforms. We're also looking at core primitives. So there's some core fundamental primitives that we have to be able to do to sort of compete in the GPU world. Matrix multiplies are examples, prefix sums, all sorts of low-level constructs which people build applications out of when they go to the GPU. And mainly that allows us then to get towards building AI or ML workloads. So come and check the code out, pull the tires. That's the wrong way around. Kick the tires, check the code out. But also, one of the things I was told was Bernard in the room, we're hiring. GPG is hiring. If you're interested in doing this sort of work, Java GPU stuff or the Babylon stuff, come and talk to us. And we always need feedback on APIs. So if you do manage to pull this out, get it to run, give us feedback on the APIs. What did you like? What didn't you like? That's always useful information. That's it. Thank you.